Hi everyone, my name is Jacob, and in this video I'm going to talk a little bit about the potential for using defects in silicon carbide as qubits. So first I want to talk a little bit about, what is silicon carbide, what's its structure and properties, and why might it be interesting to use as a qubit. So for starters, the success of the nitrogen vacancy center in diamond as a potential qubit led to an interest in studying similar defects in other materials because people realized that, well, the properties that make diamond and the nitrogen vacancy center in diamond a good qubit are not necessarily unique. There are other materials with wide band gaps and with majority spin zero nuclei that could potentially also be used and might be easier to fabricate or have other advantages. Silicon carbide is a natural place to start. Silicon right below carbon on the periodic table, and these two materials have very similar structure and properties. But there are some differences, and those are kind of the things I want to highlight and why might it be more advantageous to think about silicon carbide. For starters, silicon carbide has 250 different crystal structures that are known to exist. So if you can figure out how to use defects in silicon carbide as qubits, you might be able to change the mechanical or electrical or thermal properties of the qubit surrounding by using different crystal structures. Secondly, silicon carbide has a much smaller band gap than diamond. Diamond's about 5.5 electron volts. Silicon carbide, depending on the crystal structure, will be around 2 to 3. So this is large enough so that the energy levels of the defects that we're going to look at that are deep within the band gap won't interfere with the conduction and valence band, but it's small enough so that the optical transitions that we're going to be interested in are notably smaller than they are in diamond. In diamond, they're in the visible spectrum. In silicon carbide, depending on the defect in the structure, they'll be around 1,000 nanometers, give or take, which is much closer to the 1550 nanometers needed in optical fibers. So that makes silicon carbide promising for applications in quantum communication. And finally, silicon carbide is very important to the semiconductor industry. We know we can make big wafers out of silicon carbide. There's the capability to fabricate a lot of optoelectronic devices, photonic cavities. So that's that's another advantage. So the first question we might want to ask ourselves is which defect to use. There's a lot of defects in any material, and some might be more promising than others. This is a table with a lot of different defects, and people are looking into all of them, but the most extensive work has been done on the silicon vacancy and the die vacancy, and so those are the two that I'm going to focus on for this presentation. So I'll start with the die vacancy. There are 4 possible die vacancies owing to inequivalent lattice sites in the lattice. And those 4 different possible configurations are shown in this figure. All of them have a neutral charge. All of them have 6 active electrons, 3 from silicon and 3 from surrounding carbon atoms, which is exactly like in the negatively charged nitrogen vacancy center. And the axial die vacancies in 4H silicon carbide, as well as the 3C, any die vacancy in 3C silicon carbide, has the same symmetry as the nitrogen vacancy center, which means since they have the same number of electrons and the same symmetry, a lot of the electronic structure is going to carry over. So you still get spin-dependent polarization, which you can use for initialization and readout. And I've reminded you of the nitrogen vacancy electron structure here. This is from the paper by Gillespie that we read. So you shine a laser, you excite these electrons up to these excited states, and then they can relax back down. And the 0 spin states are pretty much always going to fluoresce when they relax back down, but there's a good chance that the plus or minus 1 spin states pass through this singlet state through a non-radiative transition. So that's what makes the fluorescence spin dependent, and that's what allows for readout of both the nitrogen vacancy center and also die vacancies. And we'll see a similar thing holds for the single silicon vacancy. The basal, what we call the basal die vacancies, which are these two, they have a lower symmetry, but pretty much all of that still carries over. The only difference is that whereas in the axial divacancies, these two plus and minus 1 sublevels are degenerate. In the basal divacancy, they're not degenerate, which means you don't have to apply an electric field to break magnetic field, sorry, to break the degeneracy. So that's actually somewhat nice. I just want to highlight this slide. This is data about the photoluminescence of these divacancies, and the thing I want to point out is that at 300 Kelvin, these sharp photoluminescence peaks disappear. So readout of the divacancy only works at very, very low temperatures, and this is a disadvantage in comparison to the silicon vacancy, which you can read out at room temperature, as we'll see. Another big advance in the readout of divacancies was in 2017. They figured out how to tune the optical excitation of the divacancies during readout to get a much higher photoluminescence contrast from 9% to 94%. So that's really important for high fidelity single shot readout. And this data is from 2014 to 2017, both showing control of spins in the divacancy and the 4H crystal structure. So that on the previous page was the first demonstration of coherent control of these spins, and they measured a decoherence time of 1.2 milliseconds, which is competitive. 2016, then there was more theory done on this. People measured 1.3 millisecond coherence time and showed that that's basically as high as you're going to get with a natural sample. But if you use isotopic purification and get rid of the carbon-13 and silicon-29 spins, you can get much higher coherence times, which has also been done in diamond. And in 2017, this group also demonstrated control of single spins in the 3C polytype with a similar coherence time. We're going to move on and talk about the silicon vacancy now. In the 4H crystal structure, there are 2 inequivalent lattice sites for the silicon vacancy. In the 3C, there's 1. In the 6H, there are actually 3 inequivalent lattice sites, but 4H is what the most work has been done on. Typically, it's negatively charged, and it's a spin 3/2 system. So that's a little different than what we've been talking about with the nitrogen vacancy center and the divacancies, but a lot of the same ideas are going to transfer over. Your qubit system is either going to be the plus 1/2 and the plus 3/2 sublevels, or the minus 1/2 and the minus 3/2 sublevels. And you'll notice here in this diagram of the energy levels that the plus and minus 1/2 and the plus and minus 3/2 sublevels are degenerate. So typically you need to apply a magnetic field to break that degeneracy, and we're going to see on the next slide with the V1 divacancy, or the V1 silicon vacancy in particular, coherent control becomes complicated because the zero field splitting is quite small, and even applying a magnetic field, you don't get that large of a breaking in the degeneracy. The initialization and readout also occurs in a very similar manner. So you can excite an optical transition, you shine in a laser, you can excite these electrons up to this 4A2 whatever excited state, and then the plus or minus 1/2 sublevels tend to decay via radiative transition, whereas the plus or minus 3/2 sublevels have a good chance of undergoing a non-radiative transition marked by this thick dotted blue line through one of these doublet states on the right. And so you get spin-dependent fluorescence. You use that for readout. You get spin-dependent optical polarization for initialization as well. So that's, again, that all works very similarly, just the numbers are a little different, but it's similar. V1 has 40% emission into the zero phonon line. That's been shown, and that's much better than the 3% that you get for the nitrogen vacancy center in diamond, or the 5 to 7% that you get for divacancies in silicon carbide. So that's an advantage for the V1 center. The V2 silicon vacancy also has an advantage in that it can be read at room temperature. Remember, that wasn't the case for the divacancy. So coherent control of the silicon vacancy has been demonstrated at room temperature. It was done in 2015 on a single spin, and they got coherence time of 160 microseconds at room temperature, which is competitive. In 2017, a group predicted that they could get T1 to 10 seconds at very low temperatures, and they used dynamical decoupling to get T2 to 20 well over 20 milliseconds at 17 Kelvin. And in 2018 is really the only study done so far experimentally on the V1 center, and they got a T2 of only 0.6 milliseconds at 5.5 Kelvin. So that's much lower, and the challenge is due to the small zero field splitting, as I discussed on the previous slide. This chart shows some comparisons of different solid-state qubit systems. You can see that the silicon carbide defects are competitive in many regards. The spin coherence time is good, better than quantum dots, not as good as the nitrogen vacancy center and diamond. And the real advantage to highlight on this page with regard to the diamond vacancies is this zero phonon emission wavelength in the infrared, as I mentioned earlier, that's very good for quantum communication and interfacing with optical fibers. Finally, we should talk about the outlook for these systems. What are its advantages and disadvantages, and what do people hope to do with it in the future? So as I mentioned, advantages are long coherence times, not as good as the nitrogen vacancy, but better than a lot of other competitors. This emission near telecommunication wavelengths. It's easy to grow, so on the right you can see these large, commercially available, you can order these on the internet, 4H wafers, and you can also make all kinds of optoelectronic devices out of these. So people are hoping to study the interfacing of qubits with transistors and other electronic devices. And finally, as I mentioned at the beginning, this versatility in terms of the rich variety of crystal structures and defects within those crystal structures that are available. And there's a lot of work that remains to be done in exploring all these different permutations and seeing what's really the best for different applications. It's been shown that you can tune the optical transition via the Stark effect, which is just applying an electric field and therefore changing the energy levels. That's important. Maybe you could use that to improve readout in certain scenarios. Entanglement with photons hasn't been fully experimentally demonstrated, but there's a lot of theory that predicts it should be possible, which is another advantage for using these things in quantum communication applications. People are hoping to integrate it, as I mentioned, into electrical devices, also photonic crystals, mechanical resonators. All of this is possible with silicon carbide. And in terms of what applications it's being considered for, pretty much everything. It has strong advantages for interfacing with quantum communication, as I mentioned, but people are also looking into the possibilities of using it for quantum communication and quantum sensing. Finally, we should talk about the drawbacks and challenges facing this technology. In terms of the DiVincenzo criteria, we have almost everything. We have a scalable qubit system, initialization and readout, and good coherence times. What we don't have is multi-qubit operations. We don't have entanglement between qubits. That's common in these solid-state defect systems. The price of good coherence is that it's hard to get the qubits to actually interact when we want them to. Another challenge or further path to look into is the possibility of using nuclear spins as in qubits. In class, we've seen that a lot of work has been done in that context in diamond. Not so much has been done in silicon carbide, but I think the outlook is promising, A, because it's been done in diamond, and B, because optical polarization of the silicon-29 nuclei, not the carbon-13, but the silicon nuclei, and coupling to both the die vacancies and the silicon vacancies has been sort of primitively demonstrated. So that's favorable. And finally, we don't know how to put qubits where we want them. We know how to get them into the material, but we don't know how to control where the defects ultimately wind up, and if we're talking about the die vacancies, what orientation they wind up in. However, because both this and the challenge of multi-qubit operations are challenges that affect not just silicon carbide defects, but also other solid-state defect qubits like the nitrogen vacancy center, work across these different communities, we'll be able to find a solution for all these technologies, hopefully. So that's all. Thank you guys for listening, and here's the references if you're interested.